All right, guys, so let's take a look. I believe we've introduced the second permutation rule, which allows us to deal with situations when I have identical objects. Okay, not just one set, but P sets. So let's go ahead and answer the question: how many permutations? Now, permutation means you have to use every object given, and you have to simply rearrange them. That's exactly what permutation is. So we can't play that sticky little game of ours where we only use 5 of the 6 or 2 of the 3 or so on and so forth. So that kind of takes care of some of the confusion from earlier in class. So we're going to go ahead and use this setup. Okay, so let's go ahead and count what n is. I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 objects. Now we can discuss the sets of R, the sets of distinct objects we have, or I should say identical sets. So let's go with S. How many S's are there? There's 1, 2, 3 S's. So R1 is 3. R2. Let's go to the T. There are 1, 2, 3 T's, so that's another 3. R sub 3. Let's go to the A. There's only one A. Okay, there's clearly some more here, so let's continue with R sub 4. The T we've already counted. We haven't counted the I. How many I's are there? There's 1, 2 I's. Okay, and then I think we've taken care of the T's, the I's, the S's, the T's, up, and then we have 1 C. So we have R5, where we have 1. Okay, so let's go ahead and substitute them into this equation and see what comes from it. So we have 10 factorial. Then I'll have 3 factorial. 3 factorial, and then 1 factorial, which is essentially unnecessary, but we'll include for now. 2 factorial, and then another 1 factorial. You know what, I'm just going to get rid of the 1 factorials because they do clump things up a little bit. So let's go ahead, and we could put this into our calculators, of course. I'm going to go ahead and just expand it out. That might actually be just as quick. Notice how I'm no longer including the 1s because, well, this is kind of silly. And it's also kind of silly that I write my 2s in 2 different ways. Something wrong with me. I am sorry, but I can't fix it. I don't know what to do. I'm just stuck with it, with who I am. Okay, so this 3 will cancel with that 3. That's easy enough. That 2 cancels with that 2. That's easy enough. 2 of these 2s will cancel with that 4. And that 3 makes that 6 a 2. Okay, so now I have simply 10 times 9 times 8 times 7 times 2. That's not so bad. 90 times 8, that'll be 720. 720 times 7. Whew, 720 times 7. Well, 700 times 7 would be 4,900, and 20 times 7 would be 140, so that must be 5,040, and then we have to multiply that by 2, so that's going to give me 10,080. You guys probably can do math better in your head than I can. I'm actually very bad at things like long division. I'm very bad at like multiplication and addition. I've always been that. I've always been that way. If you ask me right now to like do a problem like 720 times 7. Like, I would not be able to do it, I don't think. I have to, like, just count it out in my head. All right, so that takes care of that weird type of permutation where you have repetitions or identical objects. What happens if I say, I don't care about the order of things? What if we're taking a handful rather than one thing at a time, right? What if we're taking groups, not arrangements, right? Where order doesn't matter, and that does happen quite often, right? So a selection of distinct objects without regard to order is called a combination. So we usually try to be very careful with how we interject colloquial terms like combinations, because that's a word that most fifth graders know, but they certainly don't know it in the way that we will shortly. So I don't usually like presenting a formula first, but here it is. The number of combinations of R objects selected from N objects is denoted by NCR. And I want you to think of this C as representing the word choose. So we are choosing a set of things. We usually choose things. I mean, I know it's kind of silly, but I would say we don't usually choose things one at a time. We'll usually choose a set of them. Like, we'll choose a team, but we will pick players. You know what I mean? So let's continue and see what we can do. Before we go ahead and do that, notice that the only difference between this and the permutation formula is one thing, and that is this R. Okay? So let's try to rationalize that a little bit. If I put something in the denominator, what does that do to the overall number? Okay, so we're clearly increasing the size of our denominator. What would that do to any given number? Well, let's just think about it. Let's have a little thought experiment. If I had the number 10 and I was dividing it by 10, well, that's just 1. But if I was 10 and I was dividing it, say, by a factor higher, 100, then this is now 0.1. So clearly we can see with a stupid example that increasing the size of a denominator, holding the numerator constant, which is what we're doing here, we will make a smaller number occur, which is kind of what we're looking for. Because, if I'm saying it doesn't matter to me whether I have a green M&M, a blue M&M, and a red M&M, I just care if I have a blue, a red, and a green. Like, it doesn't matter the order in which I have them. Well, then, what was 6 separate different orders, right? Blue and green and red, so on and so forth. It's no longer 6, it's just 1, because I don't care the order. I just care that I get to shove those things in my mouth, right? So it doesn't matter the order. Of course, what was larger is going to become smaller. So increasing the size of the denominator decreases the number in general. And that should make sense because combinations will typically be smaller than the number of permutations. And that's not a strict rule, but it should help guide you, at least in trying to determine, am I using the right formula or not? I wasn't allowed to use a calculator when I was learning about this stuff, and so I had to kind of think of ways to rationalize the formulas. Is this the formula I use, or am I using one without R? I'd have to try and think back to these sorts of examples and remember, I want R in the denominator when I don't want as many things. Okay. For a sociological study, 4 people are chosen at random from a group of 10 people. In how many ways can this be done? So permutations is out the window. We don't care about the arrangement. We don't care about the order in which these people are chosen. So this is a 10 choose 4 scenario. So we no longer can think of this in our intuitive sense, unless, of course, you want to divide by 4 factorial. So, I mean, I guess we could kind of think about that for a moment, right? So I have 4 things, right? There's 10 possible choices for the first, 9 for the second, 8 for the third, and 7th for the fourth. But remember, I have to divide this by how many of these permutations I view as identical, right? And so I'm going to divide by 4 factorial, because that's how many things you can make identical out of 4 things. Okay, so it doesn't matter what those 4 things are. I could arrange 4 things 4 factorial ways. So I'm going to divide by that number so that we end up with what I'm looking for. Okay, this is, of course, analogous to saying 10 factorial over 10 minus 4 factorial times 4 factorial. As you'll see, this is 6 factorial and 4 factorial. The 6's would cancel with everything below the 7. And so we get the same answer. Let's go ahead and just work this out real quick. I'm going to use this because this is kind of already simplified here. 4 factorial is, of course, just going to be 4 times 3 times 2. I guess we can include the 1, or you don't have to, right? So I'm going to go ahead and cross out this 4 and that 2 with that 8. I'll cross out that 3 with that 9 and make that a 3. So it's 30 times 7. That's going to be 210 different ways. All right. Now, keep in mind that you can also use your calculator for these, and I would implore that you do so. All you have to do is go to the NCR function. I don't have a calculator on this iPad, so I can't show that to you. All right, so let's go ahead and take a look. And how many ways can you choose 2 different flavors of ice cream if the shop has 12 flavors to choose? So I think this should have been a permutation, because it totally matters if chocolate or vanilla is on top, you know what I mean? But let's just proceed as if it doesn't matter. And how many ways can you choose 2 different flavors from 12? So we have a 12 choose 2 scenario. That would be 12 factorial over 12 minus 2 factorial times 2 factorial. So this is, of course, 10 factorials. We have 10 times 9 times 8. And we have 2 right there. So clearly this will cross out with all of them. And I'll take that 2 and cross that out, make that a 6. So we have 6 times 11, so that's 66. All right, what I'd like you to do is I'd like you to do your best to complete 18, 19, and 20. And we'll compare our answers when we get back together. Again, sorry I have to be absent. I have to make these doctor's appointments when they come. Unfortunately, it seems as though this shot isn't exactly taking the kind of effect I was hoping it would take. So back to the drawing board. Anyway, hopefully you have a great day, and I'll see you soon.